Swayam Prabha. Digital India. Educated India.
Welcome to the subject Advanced Digital Image Processing and Computer Vision. Our today's topic of discussion is sparse representation. So let us try to understand the problem of sparse representation of a signal or vector. In this case, we will discuss only particularly for a vector in the discrete space, and this could be easily extended for images for a two-dimensional representation. Now, in this problem, we consider we have a dictionary of n-dimensional vectors. N here you can see that we have used the two notations. One is for capital N, another one is for small lowercase n. So the small letter n denotes the dimension of the vector, and capital N here it is denoting the number of elements in the dictionary or number of vectors in that dictionary. Now each this vector in the dictionary, they are called as atoms. So we are using a mathematical notation, as you can see here, that it's a set of atoms or set of vectors. Di is that ith atom, and there are n such atoms, and that makes a set of, say, capital D. And we should also consider that in our context that the number of element is larger than the dimension of the vector. Also, let us also assume that each atom is a unit vector. So it is not only a vector, but it is also unit vector, which means that if I take the magnitude of the atom, which we can consider as the L2 norm of the vector, that should be equal to 1. Now, if we consider any arbitrary n-dimensional vector x, then the problem of sparse representation of that vector with respect to this dictionary is to have the best linear approximation of this vector x using a subset of D as basis vectors. So the way the basis vectors are defined with we discussed about the image compression or vector compression or signal compression. It is also in the same spirit. So these atoms are acting like a basis vectors, and we can represent it as a linear combination of these vectors. Now, as you can see that it may not be required that all the atoms are used for these linear combinations. A few of them will be sufficient, and that is the sparsity. So you have again, following that alternative representations of any vector, here also we may consider, if I know this set of atoms, then only these coefficients can represent the respective vector. Or otherwise, even if I consider a n-dimensional capital, that means coefficients corresponds to each of the atom with some linear order, so that only a few of them will be non-zero. So few of them would be non-zero, most of them would be 0. That is the sparsity. So maybe some of them would be non-zero. So I am writing nz to denote non-zero. So nz, and say this is 0, which means this coefficients corresponds to d1, and say this may be some ith index. So this should be di plus 1. Say this may be jth index. This should be dj plus 1, and this is dn. So these are the set of atoms in a dictionary. So only 2 atoms, for example, in this case, is used in this representation, and their value, this non-zero value could be something like, say, 5, and say this one, say, 7, which means x can be represented as, say, 5 di plus 1 plus 7 dj plus 1 with some value of ing. So this is sufficient to have this representation. But this representation is called sparse because most of the coefficients are 0 with respect to that dictionary. So the objective here that to get this sparsity, maximum sparsity, we would like to minimize the number of atoms. So what is the best approximation? Now it could be exact representation or it could be approximation with certain bound on error as per your requirement. So the reconstruction should be as close as possible. Now as I was mentioning that this reconstruction could be exact when we consider in that case we can show that it is sufficient to have at most n atoms to get exact reconstruction if all the atoms are linearly independent in that set. So we say a set is linearly independent when if I consider here, for example, let us, without loss of generality, let us consider that we have say n such atoms which is forming this subset S. Now these are linearly independent if we consider any particular atom di. Now this cannot be expressed as linear combination of all other atoms except di. So if it cannot be expressed like this, if there exists any such atom, then the set is not linearly independent. So we can show that thing, and how it can be done. So when it is exactly n, we can always get a solution that we can easily see. So let me explain you a bit more in that respect. That consider that you have this representation D1. So here I am using the same representation, and let me define this vector as a say column vector, and consider these are the field of that vector, a component of that vector. So because it is n-dimensional vector, let me use the symbol, this arrow, to denote vector, but it's represented in the column vector. So any particular ith vector in this set S can be represented in this form, di1 to din. So you note that for the sake of convenience, I am using the row index after I because here I is representing the ith column vector, ith vector. Yeah. So we can write this expression. That means this expression we can write in this way. Say let us consider a matrix. Say these are the columns D1, D2 to Dn, and this is the coefficients A1, A2 to An. Now if I add them, if I do this matrix multiplication, it is nothing but A1 D1 plus A2 D2 plus An Dn, and this is equal to the vector x, as we know. So that is what this equation can be written in this form when we would like to have an exact representation. This equality we are putting it here. So let me write this particular matrix in the form of, say, let me write it as, say, D. So this matrix, let me write it as D, or rather D is not very conventional. Let me write this matrix as say B. Consider this matrix is B. This coefficient matrix, let me write it as A, coefficient column vector, and this feature vector is already I have written X. So the equation, what we can write, BA equals x. But you know that there are, I have to write n. I have to write n here. Now, when there are exactly n unknowns, so these are the unknowns, and what is the size of this particular matrix B? So size of this matrix B is, as you know, that each column is of dimension n. So here also you have n cross n. So in this case you have, since they are not all are linearly independent, so we can have inversion and we can get this solution. So when you have exactly the respective atoms, when you have exactly the same number of atoms, there exist one solutions in here. Now let us consider the other case. The case when you consider that if you keep the number of atoms fixed and then try to reconstruct it, and we consider here, say m could be quite less than n. Now in this situation you may not guarantee that there would be exact reconstruction. So we consider that again that same linear combinations we will be considering. But then what we should do in that case, suppose you have chosen the subset S. You have chosen a subset S already, and S, instead of having n atoms, you have, say, without loss of generality, once again let me consider there are m atoms where m is less than n. So now you see that as I have written that equation previously, so these are forming the column, these vectors are forming the column, and this is the coefficient with respect to each column vector, and that is giving my equation, giving me the representation x. Now the thing here is that this matrix, now given this atoms, this is of the size n cross m, and this is m cross 1. So this A into x. Okay, so this is the equation you get, and here you can see that number of unknown here, A1, A2, Am, that number of unknown is m, which is less than the which is actually less than the number of equations. There are n. So it is an overdetermined set of equations, because x equal to x1, x2 to xn. So there are n equations. So there are n equations, and there are m unknowns. So considering this, you have to get an approximate solution. So it is not invertible. Also, I mean that is the problem here. So you can apply the least square error technique, and there is a trick by which this solution can be easily analytically derived. So I will just show you how it is. Say if I write this solution in this, write this equation in this form, dAx. Now you multiply each side by D transpose. So this matrix I have denoted by D transpose. So now you see that this matrix is a square matrix of dimension n cross n. D transpose D is a square matrix of dimension dimension of n cross n. Okay, so it has an inversion. It could be inverted. So A equal to, you can write it as D transpose D inverse D transpose x. So this is a solution. This is called the approximate solution, and this is a pseudo inverse. This is called pseudo inverse, and the error of approximation can be written again x minus, as we have written, x minus dA. So this norm would be the error of approximation. So where the A can be again, replaced by this. So this is what, from the very standard using linear algebraic operations, you can get the solutions, get the approximations. So we can show here that if I give you a set with m number of atoms, this should be the best solution. But the problem is that which set will give this error minimum, that is not decided. So that is a combinatorial problem. Given S, I can always derive it, given S, because given S, I can derive this matrix D, and from there I can compute the solution. I can solve the problem. But the error what you get, that error, it is not guaranteed that would be a minimum. There could be another combination of atoms. They can form another subset where this error could be minimum. So the problem of your sparse representation is that to get the minimum representation, minimum set of atoms which can represent the vector as close as possible. So, and to make it more objectively, we can also determine certain error bound so that the error should not be, so this error should be less than certain bound to make it more concrete. So let us proceed with this understanding. So this is a problem what I was mentioning, the problem of approximation of a signal with the best linear combination of elements from a redundant dictionary, which means you have more number of atoms that is actually required to represent that vector with exact representation I am talking about. So it could be optimal with respect to this problem definition, or it is very difficult, as I said that it is actually a problem which is NP hard problem and combinatorially explosive. So for that we go for near optimal representation. That means with certain heuristics we try to get a solution which should be also a good approximation, and also it should be sparse. We should have the first computation, and there are another variation of this problem is that when actually this dictionary is also not given. So you would like to get both the dictionary and also the optimal representation of the signal. So this is also another problem. And when we consider that optimal dictionary, then it is not just a particular feature vector you are going to represent. It is a set of vectors for which the dictionary and its sparse representation should be optimal. So we will also discuss that problem under this particular topic. So the mathematical representation of this problem, more precise definition, that minimize the approximation error using L2 norm with m terms. So first we consider there are m fixed set of atoms, m number of atoms, and then what is the best representation from those m atoms giving the minimum error. That means maximum you can have m coefficients in this case. So this is one of the variations of this sparse approximation. So this is the optimization statement, that we are minimizing the error here. So this is the least square error part. Given particular set S, you get a minimum error, that as I have shown you already how the least square error approximation method, using the method of pseudo inverse, you can find out that set of coefficients which will minimize given a particular set of m number of atoms. But then what is the combination? Which set of atoms will give you the minimum? You have to consider that also, and that would be your solution which will give you the minimum error. Now X is a data vector here and its linear combinations already mentioned, and this is a fixed number of atoms that I have already mentioned. So first let us consider that S is given to you. So I am trying to solve the first part. I have already shown you the Liskar error method, and that itself I am again describing as a summary. So you construct the matrix B from S with the columns as elements of S. So it is the same thing what I mentioned, that you form this matrix B, di1, di2 to dim, and then this dimension should be n cross m, and then X can be represented in this form. You note that exact representation may not be possible, but we try to make as close as possible this representation. So this is basically an approximate representation. And the solution here, as I mentioned, that use the technique of pseudo inverse. So this coefficient set here I am denoting it by y, and then x equal to by, and that that you apply B transpose x, as I mentioned, just to show you, B transpose x to both the side, and then you perform the inverse of this B transpose S, B inverse, you perform that, and this will give you the solution, y equal to this. So you want this set of coefficients, which is y. Now there are two major approaches of getting this sparse representation. As you understand that this is not really solving the problem, because it is just giving the best representation given a fixed set of atoms, but it does not tell you that what is the best possible representation out of all possible set of M atoms. So some of the heuristic approaches that we would follow, one is we will be discussing, which is called matching pursuit, in particular orthogonal matching pursuit technique. The other one is basis pursuit technique. We will be mostly detailing the orthogonal matching pursuit technique. Now this or in short we call it OMP. This technique, it's an iterative greedy algorithm to get the very close approximation, though it may not be optimal, but it would give you a near optimal solution. So first what we do, that in this case we select at each step the dictionary element which is best correlated with the residual part of the input vector. So let me explain what is meant by best correlated vector, and then what is meant by the residual part of the input vector. Because it's a greedy method, so at every step what we are doing, we are representing certain part of input vector by one of the atoms and get these coefficients. When we get it, then that part of the input vector is also subtracted from the from it, and we again carry on with the residual vector. That is what is residual. So it produces a new approximant by projecting the residual onto the dictionary elements that have already been selected. So projecting is the operation which is actually measuring the correlation, which is simply the dot product of two vectors. As you know, suppose you have a vector here, let me write it as say di. So this is a vector, and this is a unit vector. We always consider a unit vector, as I mentioned, those are the dictionary element, and suppose you have x, this is a given vector. So what we do, you find out what is the component, that means take the dot product in this along this direction. So you take the dot product in the unit vector. So this direction, say this is the component of x. So what we do, we then subtract this component. That means I can say this vector is x dot di. So this is the magnitude and di, because this is along the same unit vector direction. So x minus of this, that would be the residual. That would be the residual. So once we get the residual, again we perform the same operation with some other vector or the same vector. Okay. So, how to select for which vector we will compute the residual, that is the greedy algorithm. We select that vector which gives you the maximum magnitude of this dot product. So, you take the dot product and the magnitude of it, wherever it is maximum, you select only that vector and then perform this computation. Now, this is the matching pursuit. Orthogonal matching pursuit requires some more operations, which I am explaining later. Okay, so actually extends the trivial algorithm that succeeds for an orthonormal system. So, we are doing it. Now, basis pursuit algorithm is a bit more sophisticated approach. It replaces the original approximation problem as a linear programming problem. So, we can again we will come back to just define the problem. So, let me first explain this matching pursuit algorithm, what I just discussed in just previously. As you see that here our actual objective is to get the best representation using m terms or using any m atoms, best representation. But it's an heuristics we have to apply, because otherwise it is combinatorially explosive situation. So, what we consider that first we, as I said, we are projecting residue over the dictionaries. So, we have both the term, one is residue and another is the approximate representation. That means the part which has been already taken care of, which is also part of x, accumulated part of x which has been taken care of. So, and let us consider the initialization. So, initially we will consider the whole vector x. So, initially we consider the whole vector x and that is why the residual part, which will be always operational with respect to the computation, we initialize with the whole vector x. Similarly, your approximation, since you have not done any approximation, you have not taken care of any part of x as an approximation, it is 0. Now, you consider what you are doing in general in any kth step, which means I will represent the residue by the notation rk minus 1. So, you take the inner product of k minus 1th residue, that means that at kth step you have k minus 1th residue. So, that means first step you have R0 as a residue. So, inner product of that residue, it is a vector, you should understand, that residue with an atom dj, which means you take the dot product and you consider that atom, select that atom which will be giving the maximum dot product. So, you select that atom. You note that every atom here is a unit vector. Every atom is a unit vector, that we have already assumed. So, that you should always note. So, you get these things. Now, what you do, that you simply so your approximation will be accumulated in this form, that you add that vector, this vector with this approximate vector. So, that would be the best, that is an approximation of x at that step. So, what is that vector? This is a vector di star is that vector, that is the index which has been selected, and this is the maximum part. So, which means as I mentioned, suppose this is your vector rk minus 1 residual vector at kth step, and suppose the di, this is your unit vector, say di star, which has been selected for given you the maximum dot products, which means that if I take the dot product, that means take the projection of here along this direction. So, finally, this is the vector that is representing this rk minus 1 di star or dot product of these two. This is the inner product relationship. So, this is this vector, and earlier suppose this is my approximation at k minus 1th step. So, this vector will be added with it, and you know that is a resultant vector, and this would be the vector ak. So that is this step is doing. So you go on doing these things, still no, you find that your the vector ak is very close to x. But one of the issue, as you can see, that you may again get the same, you may get the same vector at some other step. So which means that the accumulated coefficients, they finally to express as a linear combinations, these coefficients needed to be accumulated, and there is no guarantee that you can have exactly m terms. I mean, you can, it will basically continue. There is no guarantee that how many steps you require to get m terms. So you stop when you get m terms. That is the idea. So this is what I mentioned in my process. So residue also has to be updated by subtracting the approximated representation. So your RK should be then x minus AK, this representation. So, and your AK is already, now you have RK minus AK minus 1 in this step. Now you have RK and AK in this step. So this is what RK would be also considered in this. So as I mentioned, matching pursuit may select the same atom multiple times. Now, when we consider the orthogonal matching pursuit, we would like to see that every time residue becomes orthonormal to the remaining set of, to the orthonormal to the selected set of atoms, which means that if I take the inner product of those vectors, it would be always 0. So there is no point taking them under consideration. So initially, of course, you do not have any you do not have any vector. So residual vector, which is of course, and we do not have any selected atoms. So there is no question of this residual vector becoming orthonormal to any of these vectors, because your selected set of atom is also 0 and approximation is 0 accordingly. Now when you consider the kth step, so you maintain a set of atoms which has been selected. So initially it is not selected, so you don't apply that constraint. Now at kth step, what you do, you select the same way you select the I star atom which is selected, and you add them, include them into the set of already you have the set of atoms. So now what you do, for getting the best approximation of x, you need to do once again apply that least square error method. What is the best approximation? As we know already, least square error method can give you the best approximation by using that pseudo inverse technique, which means suppose Sk contains k number of atoms. Say without loss of generality, once again I form this matrix. So this is the matrix. So this is that B, and I would like to get the coefficients A1, A2 to AK, which will try to give me the best approximation of x. So the solution of this one, so if I denote it as y, it should be once again B transpose B inverse x. This is a pseudo inverse. So I have to do this computation. Then we can show actually that with this representation, your residue would be RK would be x minus, as you can see that, by. Your RK would be x minus by, or x minus B into B transpose B inverse x. So this should be your solution, and this RK will be orthonormal to all these atoms, because otherwise if there is any component that would have come under the least square, that should have been taken under these coefficients. So since now this residual error would be orthonormal. That is the interesting algebraic property which we use here. That's why none of this atom would be selected in the next step. So this form the SK. So in the next step, you only consider those atoms which are not included in SK. So here you only consider those J which is not included into SK minus 1. Okay. So that is the interesting part. That means just within M step, exactly at M step you can stop, and that is the best approximation with respect to this flow of computations. So this is what you get at this point. So you are minimizing it, and as I was mentioning that for minimization you can perform with the standard least squares techniques to solve this problem. And then you use the residual, update the residue vector or residual by this form, subtract the combination approximation from your input vector x, and that becomes your residue, and you go on doing these things. So this is the property of orthogonal matching pursuit or OMP, that it selects an atom only once as the residual is always orthogonal to selected set. For basis pursuit, let us have a very quick overview. As I was mentioning, it minimizes the approximation error using L1 norm. That is one characteristic. Earlier you have considered L2 norm, here it is L1 norm, and it can be shown it is a convex function, and hence it can be minimized in polynomial time. So this is the mathematical problem, that it tries to minimize the sum of coefficients subject to this representation. This is this problem what we are going to do. So there are different approaches to solve this problem, which I am not discussing here. So let us now consider a few exercises here. First, let us consider the following set of basis vectors or atoms in a dictionary. So you have a dictionary with 3 atoms. So first problem is to show that they form an orthonormal set of basis vectors, and you decompose a vector 1, 2, 3 as a linear combination of the outset. So you note that each vector is a unit vector. Now that was the assumptions of a dictionary. Each vector is an unit vector. Now to show that they are orthonormal, what you need to do? You need to, as you know from the definitions, there are various ways you can do. One of the simplest way, because there are only 3, you take the pairwise inner product or dot product. So always pairwise dot product would be equal to 0, but when you take the self dot product, it will be equal to 1. So that you can verify. So take any pair of vectors and perform the dot product, then it would be 0, and magnitude of these vectors is 1. Then hence a set of and also it is a set of orthonormal basis vectors. Now once we have a set of orthonormal basis vectors, then as you understand that we can, and also the vector is also of 3 dimensions, so there is an exact representation. So you can simply take the dot products along those vectors to get the coefficients. So these dot products, as you can see with respect to 1, 2, 3, that is a given vector which you would like to approximate. So for this vector it is 2 by root 3, take the dot product. For this one 7 by root 6, and for this one 3 by root 2. So now that is using this so these are the coefficients, these are the coefficients. Yeah, these are the coefficients, and these are the dictionary atoms or basis vectors. So this is a linear expansion which will give you 1, 2, 3. So because they are set of orthonormal vectors, so it is easier to compute. Let me take the second problem. Here we consider a dictionary again in a three-dimensional space consisting of following atoms. So you see that how many atoms are there? There are 4 atoms. And derive the best representation of the vector 1, 2, 3 using 2 atoms of the above dictionary following orthogonal matching person. Now let me first tell you that in our assumptions we considered each one of these atoms should be unit vector, which is not here. So we have to normalize them. But we can avoid normalize here because you know that because they are all of equal magnitude, because if I take the magnitude, their magnitude is √3. You can check. So 1 square plus 1 square plus 1 square for each one of them. And then now for unit vector, it is basically 1√3 multiplied by this, vector, that is unit. So since it is always 1 by √3, so we will be simply ignoring this part while doing expansion just for the computational. Yeah. So the selection, so let us consider now first selection of an atom. So what we will do, we will take the dot product with the input vector with all the three atoms and see where you get the maximum. Once again note that magnitude becomes the same, that's why I am not taking unit vector. So the first one, like 1, 1, 1 gives 6, and actually it is found to be maximum. If you take the dot product of others, so for example, let me consider, say 1 minus 1, 1. So if I take dot product with 1, 2, 3 and 1 minus 1, 1. So we know that it would be 1 minus 2 plus 3, that is 2. So it is less. So you can do for all other vectors and you can see that 6 is maximum here. So therefore, we can consider R1 is 1, 2, 3, that vector x. So this is the vector x minus this 6 into this. So the second selection, we will find this is the maximum. So this is your residue. Now this is a maximum. You choose one, but now what you do, you take the least square approximation using these two. So there, this normalization part is making no difference. So you take the least square error method solution, because maximum 2 we have considered, and for approximating, what we consider that we form the equations as we have mentioned, that this should be the equations. Say this is the respective, so chosen vector. So this is your, say, D1 and this is your D2. These are the two vectors. So that forms the matrix B, and this is your coefficients. See, X and Y, they are your coefficients here. Okay, so this is the matrix Y and this is your X. Okay. So what you need to do, you need to perform the pseudo inverse of B. So we are saying this is A rather B. So this matrix is A and this is so finally you see that this is a pseudo inverse, A to A inverse AT, A transpose A inverse to A transpose 1, 2, 3. That is the solution. And to perform the operations, you get, first you compute A transpose A, and then A transpose A inverse is 1 by 10, and so this is given by this A transpose A inverse. So the solution is that xy, this is the coefficients, 18 by 10 into 6, 10, and since you are taking these are the vectors, so finally this is your solutions. Now if I take the normal vector, so all of them should be, you have to multiply √3, and this should be 1 by √3. So in actual, when we are getting the sparse representation in your atoms should be unit vector. Just for the specification of this problem, we have done it in this way. So with this, let me stop here, and we will continue this discussion for sparse representation in the next lecture, where we will see that for a given set of input vectors, there is a method by which we can get a near optimal solution for a suitable dictionary and its sparse representation. So let us stop here today. Thank you very much for your patience and listening.